The online training is an initiative of Microsoft to teach its existing users how efficiently they can use Midas Civil. We are going to organize a lot of sessions after this session, and in the subsequent sessions we are going to talk about specific type of bridges. In the next session we are going to talk about construction stage analysis in Midas Civil and what are the different features that are associated with construction stage analysis and how you can model construction stage analysis in Midas Civil. Today we are going to do a very basic training on Midas Civil, the different geometric features that we are going to use and how the different geometric features can be used to model the geometry of the bridge. So let's get started with the Midas user online training first. These will be the contents of my training. I'll be talking about the different modeling features, the different boundary conditions, the different loading features, analysis results, and then I'll be talking about the design features and the miscellaneous items. First of all, let's talk about the overview of Midas Civil. Midas Civil is a 3D structural analysis and design software based on finite element analysis. These are the different structure types in which you can employ Midas Civil for analysis. You can use Midas Civil for conventional bridges such as slab covered bridge, frame bridge, arch bridge, integral bridge. You can use Midas Civil for girder bridges such as composite precast girder bridge and composite steel plate girder bridge. You can use Midas Civil for segmental post-tension box girder bridges. You can use Midas Civil for cable bridges such as suspension bridge and cable stayed bridges, and you can also use Midas Civil for rail track structure interaction. You can use Midas Civil for underground structures such as subway station and purification plants. You can use Midas Civil for soil structure interaction. You can perform nonlinear static and nonlinear time strain analysis. And as far as the seismic analysis is concerned, you can do response spectrum analysis, Pushover analysis, inelastic time strain analysis, nonlinear time strain analysis with damper or isolator. Multiple support excitation is also supported. If we talk about the detailed analysis such as CFD analysis, cracking analysis, fatigue analysis, interface nonlinear analysis, or the contact analysis, we have another software called Midas FEA, which is used to do this kind of analysis, and we have developed an interface between Midas Civil and Midas FEA, and you can export the models from Midas Civil to Midas FEA to perform the detailed analysis. These are the different analysis types that are available in Midas Civil. We can perform moving load analysis, construction stage analysis, P-delta, buckling, pushover, time strain analysis, and response spectrum analysis. So this slide lists all the analysis that can be done by Midas Civil. This is the element library of Midas Civil, the different 1D elements available in the form of truss, beam, etc. The different 2D elements available in terms of plate, plane stress, plane strain, etc. And in Midas Civil you can also model solid elements. The solid elements can be either 4-node, 6-node, or 8-node solid elements. So first of all, let's get started with the graphical user interface of Midas Civil. Let me briefly talk you about the graphical user interface. For talking about the graphical user interface, I'll take you to the program itself and I'll show you some of the graphical user interface features of Midas Civil. So this is how the work window of Midas Civil looks like, and on the left hand side we have a tree menu. Inside the tree menu we have the menu bar. You can access any menu from here. So let's say you want to define a material. You can either define the material by the tree menu, or you can go to model, properties, material to define a material. Similarly, you can also go to properties by right clicking in the model window and go to material for defining the material. Similarly, from the tree menu you can go to geometry and you can go to properties and material to define the material. So in a way you can access the same option from 3 different places. You can either go to the menu bar at the top, or you can go to the tree menu on the left, or you can just right click in the model view to go to properties or any other option you want. Let me quickly open a model in front of you and I'll show you different graphical user interface features that can be used in Midas Civil for performing analysis on bridge structures. In the tree menu, we have a very special option called works tree. As you can see on your left, this is the works tree, and the works tree will list all the work that has been done in the model so far. So as you can see here, I have defined 1900 elements, 631 are beam elements, and 1280 are plate elements. I have 3 different materials, 6 different sections. I have defined some tapered section group, some thickness, and these are the different supports that I have assigned. So let's say you want to select some elements which have the steel material. So you can just double click on the steel material to select all the elements which have steel material assigned to them. If you want to select the elements having composite section defined, you can just double click on the composite section and the composite section elements will be selected. You can see the supports by right clicking on the supports. As you can see, these are the 2 supports that I have assigned to this structure. I have defined certain point spring supports which can be obtained by going to the support and displaying it, as you can see here. If you want to see the properties, you can just go to the properties, right click, go to the properties and see the definition of the springs. If you want to see the loads, just right click on the load and you can see the load that has been assigned and how the load has been assigned. You can also see the moving load data here. You can display the different lanes that have been assigned to the model. As you can see here, I have defined 2 lanes, and if I zoom in, you can see that the 2 lanes have been defined at these 2 locations. So this is simply everything about the graphical user interface of Midas Civil. I'll be talking in details about the graphical user interface by modeling a similar kind of bridge in Midas Civil. But before that, let me talk about the different features of Midas Civil. It's in AutoCAD, then you can import it as a beam elements, and solids cannot be imported. The last thing that I would like to tell you about the import from AutoCAD is that the unit system must be consistent. So when you are importing a line, let's say from AutoCAD, if you keep the unit system as meter, then all the units that you have defined in AutoCAD will be imported as meter. But if you have defined the unit system in AutoCAD as millimeter, then before importing, change the unit system of Midas Civil as millimeters. Now these are the different material properties from several codes that can be defined in Midas Civil, and you can also define the time dependent materials as per these codes. These are the different sections that can be defined in Midas Civil. You can define the standard sections such as the I section, composite section can be defined. You can define the SRC sections, the pre-stressed composite section, and the user defined sections is also supported. Now let me talk about the section definition in detail. The section can be defined under the properties menu of the model, and once you go to section, you have a lot of options to select from. As you can see, you can either select the I section, the T section, the box section, etc. And if you want to define the section from the database, you can select the code and then you can select the section name. Now once you select the section name, the properties of the section will be automatically taken into account. So here, let's say I want to define this section, I can just click on OK and this section will be defined. Similarly, you can define the combined sections, the pre-stressed concrete section, the tapered section, and the composite sections can be defined. In the pre-stressed concrete section, we have an option here, as you can see, the mesh size for stiffness calculation. Now many of you must be wondering what is the importance of this option. Now let me show you what is the importance of this option. For the determination of torsional moment of inertia and the effective shear area, Midas Civil first generates a meshed element of length 20 meters and it applies a load on the tip of the cantilever beam, and based on the rotation in the torsional rotation, it determines the torsional moment of inertia, and the effective shear area also is calculated based on these. So if the torsional moment of inertia is not as per your expectations, you can change the mesh size and the torsional moment of inertia will be changed. So if you are not happy with the torsional moment of inertia calculated by Midas Civil, you can change the mesh size manually and you can try to move the torsional moment of inertia as per your needs. You can create the elements using node to node approach, or you can create the elements using the grid approach. Now let me show you what these two approaches are. The first approach is you can create the nodes and then you can join the elements by those two nodes. So here I am creating two nodes. So as you can see here, I have created two nodes, and if I want to create an element between these two nodes, I can go to Model, Element, Create Elements, and I can click on these two nodes to create the element. The second option is I can create the grid, and in this grid I can just click on any 2 points to create the beam element. And similarly I can create the plate elements also. If you want to create the curved elements, then you can create the curved elements by going into the curve elements creation option in Midas Civil, which is available under the elements option. So if you go to Model, Elements, you can select the option of Create Line Elements on Curve, and here you can create the curved elements by selecting any of these options. So as you can see here, you can select the option Arc by 3 points, where you can select 3 points and Midas Civil will generate the curved element for you, or you can define the curve by 4 points, you can define the curve by center and 3 points, etc. So based on your needs, you can define the curve element accordingly. You can also use the extrude feature, which can be used to create an element out of a node. You can create a plate element out of the line beam element, and you can create a solid element out of a plate element. We are going to use this feature when we will model the bridge. This is the change element parameters option in Midas Civil. We can change the several parameters of the element from works tree, from the element table, or from the change element parameters option. Now let me show you how you can use these three features. If you go to the works tree, let's say we have 3 different beam elements as shown here. If I want to change the materials, I can just define, let me define one material. If I want to assign this material, I can just select the beam elements and drag and drop this material on these elements to change the material properties. If I want to change the section, I can just select these elements again and I can drag and drop any section and the section will be changed. If I want to change the same things through the tabular input, I can right click on the elements and go to tables, and I can change any property as you can see here. So if I want to change the section property, I can put in the section ID. If I want to change the material property, I can put in the material ID. If I want to change the type of the element, then I can click on the drag on the drop list and I can select what type of element is it. The third option is you can go to Model, Elements, Change Element Parameters, and here you can change material ID, section ID, as well as you can change the element local axis, element time. You can also align the element local. So let's say I want to change the element local axis of this beam element. I can select this beam element, define the beta angle, and once I change the beta angle, as you can see, the orientation of element has changed. So this is how you can use this option to change the parameters of different elements. In Midas Civil, you can define the mass as per these two types. You can either define the automated mass using the mass density of the elements, or you can define the additional mass using the nodal mass, or you can convert the loads to masses. Now let me show you how you can define the mass in Midas Civil. For defining the mass automatically, you can go to Model, Structure Type, and you can convert the self-weight into masses by checking on this option. So this option will convert the self-weight into masses. The second option is you can define the mass by using the nodal mass approach. Here you can define the mass in the X, Y and Z direction, as well as the rotational mass in X, Y and Z direction. Thirdly, you can define the mass by converting the load into mass. Here you can select what load case do you want to convert to mass, and the load case will be converted to mass. Generally, when we define barriers in our bridges, then we convert the barrier load into mass, because when earthquake happens, then the mass of barrier will be taken into account for calculation of force on the structure, and hence you can convert the barrier load into mass by using this option. Now let me take you to the tutorial that I have sent you guys, and we will model the same bridge in Midas Civil. So as I have sent this tutorial to you guys, this is the step-by-step tutorial that I am going to do today, and we are going to model the geometry of this bridge, and then we will define the supports on this bridge, and then we will define the load on this bridge, and finally we are going to define the moving loads for performing the analysis. Now for modeling this bridge, this kind of a bridge in a finite element analysis software, we have three different options. The first option is to model the bridge using the solid elements. The second option is to model the bridge using the plate elements. Here I can model the deck using the plate elements. I can model the beams using the plate elements, and abutment can be modeled using the plate elements, etc. And the third approach is the Grillage Model approach. So let me talk about these three approaches briefly. As you can see here in the solid element modeling, I will define the girder and the deck plate as solid elements for performing the analysis. And this is an example of FEA modeling based on solid elements, and this shows the stress distribution, how does the stress changes inside an element for this kind of modeling. The second option is you can go for plate element model. Here I can model everything using the plates. And the third option is I can go for the Grillage Model approach. In the Grillage Model approach, the deck is idealized as a series of beam elements or grillages connected and restrained at their joints. So this is what it means by Grillage Model approach. Here the deck is continuous on the top of steel girders, and I have idealized the deck and steel composite section by the line beam elements in the longitudinal direction, and in the transverse direction I have used the section of the deck for modeling the transverse beam. As we know that the bridge will have stiffness in the longitudinal and the transverse direction, the composite section will take care of the stiffness in the longitudinal direction, and in the transverse direction the transverse beam elements that we have defined will take care of the stiffness of the bridge in the transverse direction. This is generally how the Grillage model is made. Let's say this is a deck element. This is the deck cross section, and the width of the carriageway is 7.4 meters, and I want to model this deck in Midas Civil or any other finite element software using the Grillage Model approach. So what I'll do, I'll divide the deck at certain places. As you can see here, the dotted lines represent where I have cut the cross section for modeling a line beam. After I cut the section at several locations, I will make individual cross sections representing this the area between the dotted lines. So for this type of carriageway, I will define 9 different type of sections, and then I'm going to define a grillage model out of this sections that I have defined. So let us start the modeling of the bridge that I have shown you earlier. We are going to model a curved composite girder bridge. The first step to model the bridge is to model the material and the section properties. So let us model the material and section properties. I am going to follow the steps that I have outlined in the tutorial, and you guys can just watch it right now how I am doing the maneuvers for modeling the bridge, or if you want to do it with me, you can also do it. So first I will open a new project in Midas Civil. Let me save the project with some name. The first step is to set up the unit system. You can set up the unit system by going to Tools, Unit System. Let's say I want to set up the unit system as Newton kilonewton, meter kilonewton. So I'll set up the unit system as meter kilonewton here, and I'll define the material properties. For defining the material properties, as I've said before, we'll go to Model, Properties, Material. And first I will define the concrete material. The concrete material that we are going to use for the deck and the abutment and the piles will be grade C4000. So I'll select the database as grade C4000, and once I click OK, the material will be defined. Now I will define the material for the steel. For that I will go to ASTM 2009 steel code, and I will select the material database as A53. Finally, I will define one more concrete material which will have the same properties as that of grade C4000, but the density will be 0. The reason why the density will be 0, I'm going to explain later while I'll do the modeling, but as of now I'm using a 0 density material which has the modulus of elasticity same as grade C4000, and hence I have renamed this material as grade C4000, density equal to 0. So in this way we have defined 3 different materials. We can go to the works tree to check whether the 3 different materials have appeared in the works tree or not. And as you can see the works tree, the 3 different materials have appeared. So as of now we have covered these 3 pages of the tutorial, and now we will define the different sections that we are going to use for the modeling of the bridge. I'm going to define composite section, rectangular section, double angle section, tapered section, and circular section. The composite section will be used to model the stiffness of the deck and the girder in the longitudinal direction. The rectangular section will be used to provide transverse stiffness provided by the deck. Double angle section will be used to model the cross frame. Tapered section will be used to model the pier cap, and the circular section will be used to model the pier and the piles. So let's get started modeling the bridge by defining the sections. For defining the section, I want to change the unit system as inch and kips. So I'll go to Tools, Unit System, and I'll change the unit system as inch kips. A general introduction to this tutorial: everything written in red is the path that you have to follow to reach to a particular dialog box. So here I will go to Tools, Unit System to reach to this dialog box. So in Midas Civil I'll go to Tools, Unit System, and I will select the unit system as inch kips, and I'll click on OK, and you can see that the unit system has been changed to inch kips. If you want to change the unit system by directly, then you can just select the unit system from here, and once you select change the unit system from here, it will be automatically updated here. So let's define the composite section. For defining the section, I will go to Properties and I will go to Section, and the first section that I'm going to define is the composite section. I'm going to define a steel I type of composite section. I will define the full slab width. Then I will define the parameters for the slab. And then I'm going to define the material for the slab and the deck. So this is the concrete material, and for the steel material I'm going to select A53 in the database of ASTM09 code. So in this way I have defined the composite section, and you can see in the tutorial I have provided the steps that you have to follow. You will go to Model Properties section, you will click on Add, and then you will go to the Composite tab. As you can see here, you will give it a name, the section type, etc. And by doing these steps you will be able to define the section. Now let's define the second section, which is a rectangular section for modeling the transverse stiffness of the bridge. So we are going to define a solid rectangle section, and we will give it a name, transverse section. So the type will be solid rectangle. As you can see here, I will give it a name, transverse section, and I will define the properties like this. Now you must be wondering, why did I take the depth of the section as 9 inches and the width of the section as 132 inches. The depth of this section will be the depth of the deck, because we are going to model the stiffness of the bridge in transverse direction, which primarily comes from the deck, and hence the depth of this section will be equal to the depth of the deck. And the B will be the spacing between these cross members. So whatever the spacing between the transverse members will be, the width should be equal to that spacing. Now I'm going to define the file section, which is a round section, and the diameter is 12 inches. So I'll go to the solid round option. I will give it a name, file, and the diameter will be 12 inches. Now I will define the cross frame section. For that I will go to the double angle section. I will give it a name, cross frame, and I will define the properties. So here you can see the parameters, what all parameters that you have to define. And now I will define the tapered section for the pier cap. For defining the tapered section, I have to go to the tapered section tab. As you can see here, I will select the tapered section type as solid rectangle. I will give it a name, pier cap, and I will define the properties for the pier cap. And here I will define how does the z-axis variates, and I have selected the type as linear, and I will change the offset as center top. And now I have defined the pier cap. And finally I'm going to define the properties for finally we are going to define the properties for pier, which is again a solid round, and the diameter is 120 inches. So as you can see here, the final section that we are going to define is the pier section. For that I will go to solid round again, and I will give it a name, pier, and I will define the diameter as 120 inches. So in this way we have completed the definition of the materials and the sections. Now we have to start the geometric modeling of the bridge. For doing the geometric modeling of the bridge, I'm going to use the unit system as fit kips. So I'll again change the unit system. I'll change the unit system as fit, and the kips is already there, so the unit system has been changed. Now let me brief you about how I'm going to do the modeling. For doing the modeling, I will first create two nodes. The node which is at the origin is the center of the bridge in a way, and then I'm going to model different nodes by rotating this node by different angles, so that I can create the curved profile of the node. So as you can see here, after creating the first two nodes, I'm going to rotate the second node with reference to the center and rotating it by 2 angles to get more nodes. So as you can see here, I first created these two nodes and I rotated them by 2 angles to create more nodes on the same profile. So let me do this maneuver in Midas Civil. You can define the nodes by going into the nodes, create node option, and I will define one node at origin and I'll copy it by 400 feet in the Y direction. This is the top view and you can see that two nodes have been defined. So this is node 1 and node 2, and the distance between node 1 and node 2 is 400 feet. Now I'm going to rotate node number 2 with respect to node number 1 by certain degree. For that I will go to Model, Nodes, Rotate, and I will select node number 2. I will rotate it by unequal angle based on the geometry of the bridge, and I will define the first point as the origin. So as you can see here, I have rotated this node by 20 degree and 40 degree to get two more nodes. Now I'm going to translate these nodes in the direction of in the axial direction, and the direction will be defined by the direction of node 1 and node 2. So for that I'm going to go to Nodes, Translate Nodes, and I'll translate them by unequal distance and the direction will be arbitrary. So this is how I'm going to translate it. I'm going to select this node and the direction vector will be from node 1 to node 2. Now once I click on apply, you can see that more nodes have been created. Similarly, I have to create the nodes for other parts of the bridge. So I will define the direction vector as the direction from node 1 to node 3, and similarly I'll do the same thing for the node number 4. And in this way, let me zoom in at this location. You will see that I first created this node and I rotated this node to make these two nodes, and then I translated this node by a direction defined by the origin node and this node to create 4 nodes more. And similarly I did the same thing for the other 2 nodes. The purpose of doing it was that we knew the radius of the bridge and we knew the angle. So with the help of the angle and the radius, we have defined the first node. Then with the angle we defined the other 2 nodes, and we translated those 2 nodes in the transverse direction of the bridge to create more nodes. Now I'm going to rotate the center nodes by certain degree so that I can model the pier below it. It's a bit skewed by 20 degrees, so I will rotate these nodes by 20 degrees. For rotating, again I'll go to Model, Nodes, Rotate Nodes, and I will rotate it by an equal angle of 20 degrees. I will rotate it about ZZ axis and I will select the first point as node number 10. So let me zoom in so that you can see it in a better manner. So I will I'll click on the first point field here, and when it becomes green you can select any point from the model. I'll select node number 10 and I will choose the option as move. I'll click on apply. So in this manner I have rotated these nodes by a certain angle to model the skew in the bridge. So up till now we have covered these different steps, and now we are going to model the super elevation in the bridge. For modeling the super elevation, I will first select the exterior nodes and I will move them up by the required super elevation, and then I will project the middle nodes to the line defining the first node and the super elevated node. So let me show you how we can do that. So first of all, I'm going to select the nodes on the far end of the bridge. As you can see here, I will go to Model, Nodes, Translate Nodes, and I will move them up by 2 feet. So in this way, I am providing super elevation to the end nodes of the bridge. And now I am going to project the middle nodes along the line defined by the first node and the last node, so that we can have a smooth super elevation from interior end of the bridge to the exterior of the bridge. For that, I will go to Model, Nodes, Project Nodes, and I will project the nodes on a line. I will define the line by clicking on this and the exterior node. As you can see here, the first node is located at 0, 400, 0 coordinate, and the second node, which is the node at the far end of the bridge, is located at 0, 440, 2. So that means we have provided a super elevation of 2 feet to this bridge. I will select the middle nodes so that they can be elevated by certain angle by projecting them to a line. I have to move this node, so I will select the move option and click on apply. Similarly, I'll do the same thing for other nodes so that I can apply the super elevation to the middle nodes, and similarly for the third set of nodes. So in this manner, I have provided the super elevation to the nodes. I can check what super elevation has been provided to what node by simply clicking on the node, and you can see that the Z coordinate of this node has been modified and it has taken care of the super elevation that we have provided to the bridge. Similarly, this node has been provided by the Z has been moved up by this much feet, so that the super elevation has been modeled. So up till now we have modeled the super elevation of the bridge, and now we are going to model the curved beam element so that we can model the curved superstructure of the bridge. For that, I will go to Model, Elements, and I will create line elements on curve, and I will select the arc by 3 points. I will define the material as the steel material, the section as the composite section, and I will click on 3 nodes to create the curved element. In the finite element analysis, the finer the element is, the better the results are. So for that, I'm going to model this curved element into 40 different segments, and I'll again select the different nodes, and as you can see here, in this way the element has been modeled in 40 different elements. Similarly, I will do the same thing for other nodes, and as you can see here, I'm modeling the full width of the bridge. So as you can see here, I have modeled the superstructure of the bridge, and if you go to the tutorial, you can see the same thing that I have done here. You need to change the material to the steel material, then you can click on point 1, P1 here, and you can select the nodes 2, 3, 4 successively to create this curved element. Similarly, you have to create the curved elements in the transverse direction by selecting the other nodes. But now there is a catch. The catch is, when you create the curved element using this option, it might happen that it misses some of the nodes, and the probability is it will miss the nodes which are previously defined. Because we have defined the number of segments as 40, so depending on the length of the element, it will divide the element into 40 different segments, and it is how it will create a segment. So if you see this element here, you will realize that it has missed this node which was previously created. So the node number 9 was previously created, and this element has missed this node. So what we are going to do, we are going to divide these elements by these nodes, and you can see that step in the tutorial also. We will go to model elements divide, and we will set up the element number and the node number from which the element has to be divided. So we'll go to model elements divide element. We will select the element number. First we will select the divide by node, element number and the node number. So here I can activate the element and the node number. So this is element number 55 and this is node number 9, and once I click OK, you can see that the element has been divided into two different elements for joining at this node. So now they have two different elements. Similarly, for element number 95 and node number 10, we are going to do the same thing. Now you can see that the element has been divided at node number 10. And similarly, for element number 135 and node number 11, we are going to do the same thing. And once we click on apply, you can see that the elements have been divided. So in this way you can check whether the modeling has been done properly by Midas or not by checking at the elements where the node was previously defined. And once again, when you define the number of segments in create elements field, here when you define the number of segments as 40, then depending on the total length of the element, it will divide the element into 40 different segments, and it might happen that the nodes that are previously used to define the arc might be missed, and those nodes you can manually check by clicking on the element and clicking on the node. And if the node is not divided, if the element is not divided at that node, then you can divide it manually by going into model element divide element and divide by node. So till here we have covered the superstructure modeling in the longitudinal direction. Now we want to model the transverse elements. For modeling the transverse element, we will use the transverse beam elements, and we will define the material grade as grade C4000, density equal to 0. Now let me talk about why we have chosen the density as equal to 0 for the transverse beam elements. Now if I see the 3D view of this for what we have modeled so far, you can see that here we have the steel girder at the bottom, and then we have the concrete deck on the top. Now what it means is the self weight of the bridge at this moment is the weight of the steel girder and the weight of the concrete slab on the top. And now what we are going to do is we are going to model the transverse element which represent the transverse stiffness of the deck. And if we define the density as non-zero to those elements, then the self weight of the slab will be duplicated. So that's why I have defined a material which has the same stiffness as that of the deck element, but the density is 0. So now let's model the transverse elements. For that I will go to model elements, create elements, and I will define the material as grade C4000, density equal to 0, and the section as the transverse section. And now I'll click on two nodes to create the transverse elements. Now this is a curved bridge in which you will have to manually define all the transverse elements, but if it were a straight bridge, then you could have defined only one transverse element, and you could have copied that transverse element along the length of the bridge to model other transverse elements. But since it is a curved bridge, it is not possible to translate it automatically. So I will just click on the nodal connectivity field and I will manually define the transverse element. So I'm clicking on the first node and the last node to define the transverse element, and we can check on the node number, the element number, to see the number of new elements that is being created. So here I am creating the new elements, It's not a very difficult task. You can just click on two nodes and the transverse elements will be automatically created. So here, this is how I'm creating the transverse elements. For those of you who are very familiar with Midas, they will know that if you are dealing with the straight bridges, the bridges with little skew, then you can just create one transverse element and then you can copy that transverse element along the length of the bridge to model other transverse elements. But since it's a curved bridge, it's not possible to do that, and hence we can just do it element by element. Now as you can see, we have completed the grillage model for the superstructure. The grillage model has the stiffness of the bridge in the longitudinal direction, which are represented by the composite sections, and the transverse stiffness of the bridge is taken care of by the transverse elements that have the section properties of the deck slab and the material properties as the material properties of the slab, but with density as 0. So in this way we have modeled the superstructure. Now let's model the cross frames. For modeling the cross frames, what I'll do, I will translate some nodes by certain distance and then I will model the cross frames. Now in the tutorial I have mentioned that what all nodes that you have to take, that you have to select for modeling the cross frames. But in this session I'm just gonna select some nodes and I'm gonna show you how the cross frames can be modeled. So here I'm selecting these nodes. You can use the dynamic rotation feature of Midas Civil and you can, so here you can see that I have modeled, I'm using these nodes. And finally I'm copying these, the end nodes to create the cross frame. So now I'm going to translate these nodes in the Z direction so that I have another set of nodes to create the cross frames. So I'll go to model, nodes, or let me just take the tutorial example so that we are on the same lines. If you guys are following me, then you can just we can be on the same lines basically. So I will just copy the definition from the slides. I will just paste it here and you can see that these are the nodes that you have to select as per the tutorial that I have provided you. So if you just copy these node number into Midas Civil, then Midas Civil will automatically select these nodes and you can put in the number in the node selection field, which is here, and the nodes will be selected. Now I will go to model, nodes, translate nodes, and I will translate them by 3.5 feet to create a new set of nodes. So let me zoom in at the location. So as you can, so here you can see that the nodes have been translated in the direction of the gravity, and we have a new set of nodes to model the cross frames. So here is how you can see that I have modeled the new nodes. Now I want to model the cross frame between the two nodes. For modeling the cross frames, we first need to model the rigid links. Now why do we need the rigid links? Because the new nodes that we have translated, that we have obtained after translating the old nodes, they still lie in the same section. Because when you see in the reality, the section has certain depth, it has certain width. But for the grillage model purpose, we have assigned the section properties to a line beam element, and when you do so, you will lose the depth of the section and the width of the section. So in order to take into account that the cross frame has been connected to the same element, we have to define a rigid connection between the new nodes that have been generated and the old nodes that were previously there for the element. For that, I'm going to go to Model, Boundaries, and I'll go to Elastic Link, and I will define the rigid type of elastic link, because there will be a rigid connection between the line beam element and the node that we have obtained now. And you can define the elastic link by clicking on the two nodes. So here you can see that I am defining the elastic link by clicking on the two nodes, and this is how you can model the elastic links. Similarly, I will do the same thing for the other part of the bridge. Now again, since it's a curved bridge, we cannot copy the elastic links from one location to other location. But if it were a straight bridge or a bridge with little skew, we could have done it easily. And hence I am defining the elastic link manually. So you can just click on the two node selection field here and go to the location where you want to define the elastic links and click on those two nodes, and the elastic link will be defined. And finally, the elastic link for the end support. So in this manner, I have defined that the new nodes that I obtained are rigidly connected to the line beam elements. And now I'm ready to model the cross frames. For modeling the cross frames, I will go to Model, Elements, Create Elements, and I will select the section as the cross frame section, the material as steel material, because the cross frames are made of steel, and I'm going to create this cross frames by clicking on the two nodes separately. Here I will uncheck the option intersect element and node, because the cross frame that I'm going to model, they don't have connection between them. So for that I uncheck the option intersect node and element. And now I'm going to click on individual nodes to create the cross frames, and this is how the cross frame profile looks in reality. Similarly, I'm going to model the cross frame in other parts of the bridge. Now let me just activate the parts of the bridge where I want to model the cross frame. So I will select the nodes at several locations. So let me select the nodes here at this location, select the nodes at this location, then select the nodes at other locations where you want to model the cross frames. Now I have selected a part of the model, and I can activate this part of the model to generate the modeling only on this part of the model. So here you can activate a single part of the model by going to Activation and select the activated selected. So here I think you can see that it's now very easy to model the cross frames. I can just select the nodes here. I don't see the part of the structure where I'm not interested in, and I can do the modeling simply like this. Similarly, I can create the cross frames for other parts of the bridge. Similarly, when you do the tutorial by yourself, you can activate a simple part of the bridge to do the modeling so that it becomes convenient to do the modeling. And as you can see here, now I'm creating the other parts of the cross frame. It's a bit mechanical task, and I hope that you guys can just sit back, relax at this time and see how the cross frames have been modeled. And finally we reached the last end of the bridge, and this is how we have modeled the different cross frames. So as you can see here, we are done with modeling the cross frames, and now we can activate the whole structure to see where the cross frames are located. Now, as I said before, the bridge is a bit skewed in middle, and we have a pier whose major axis is not aligned as the major axis of the deck at the top. So I'm going to model the cross frames at that location also. For that, I will select the nodes which I want to translate. So these are the nodes that I want to translate. Let me activate these nodes, and I will select these nodes again, and I will translate them in Z direction by 3.5 feet, and I will create the cross frame between these elements. So for creating the cross frame, again I will go to model elements, create elements, and I will select the material and section properties for the cross frames, and this is how I am creating the cross frames. We need one more node here which has not been activated, so we can just go back and do the modeling in the full view of the model. So this is how we have modeled all the cross frames that are required in the bridge, and I hope you can see that we have modeled the cross frames at the locations where I want to have the mid supports and in the intermediate mid spans. Now for the new nodes that we have created, we need to connect them through the rigid link again, because again they are the part of the same section. For that I will again go to model, boundaries, elastic link, and I will select the type as rigid, and I can select the nodes. So I'm selecting the node by clicking on two nodes option here. It's a bit untidy, the structure is a bit untidy at this location. So if this is the case, you can just activate that part of the structure so that you can play around with it. Now let me just activate these two nodes, and these two nodes. And when I activate it, it becomes more convenient to work with. So I need the elastic links at these two locations, and if I activate the whole superstructure now, it looks okay. So now you can see that I have modeled the deck, I have modeled the girder at the bottom of the deck, and now I have modeled the cross frames also. The next step is to model the pier cap. For modeling the pier cap, I will first translate some nodes from the bottom of the cross frames by 1 feet, and then I will create the pier cap by joining the nodes that I will get after translating the nodes at the bottom of the cross frame. So for that I will first select the nodes. So I can just select the nodes as written here, or I can just go to the model view and just copy the nodes here. So here I am selecting the nodes where I want to create the pier cap, and similarly I want to create the pier cap at this location. So I'll copy these nodes. So I have selected these nodes, and I'll translate them in the Z direction by 1 feet. So now I will select only the elements that have been recently created. That can be done by clicking on this option, which is select recent entities. You can just press Ctrl and R to select these recently created elements, and now I have activated the recently created elements. Now I want to create the pile cap, the peer cap on by these nodes. For that I will go to Model, Elements, Create Elements, and I will go to the type of material will be grade C4000 and the section will be the peer cap section. Here I will check on intersect node and elements, and this is how the peer cap will look like. Now as we know that the peer cap should have a smooth transition from the section property at this location to the mid. So what I'll do, I'll use the tapered section group option of Midas Civil, and I will select the elements which are in a tapered section. Similarly, I will select these elements and I'll give it a different name, and the same thing will be done for the second pair. So in this manner I have obtained the tapered profile of the piers, and now I'll activate the whole structure, and this is how it looks like. So as you can see, in the middle we have a skewed pier, as you can see, and now I'm going to model the piers. For modeling the pier, I'm going to use the extrude feature of Midas Civil. I will select the nodes at the bottom of the pier cap and I will extrude them in the Z direction to create the pier elements. So I'll select this node, and the next node will be this node, and I'm going to use the extrude feature of Midas Civil to generate the pier elements. For that I will go to Model, Elements, Extrude Element, and I will extrude it by 40 feet, and the element size will be 4 feet, and I will assign the properties of the pier. Now once I click on apply, you can see that the pier has been modeled. So up till now we have modeled the superstructure, we have modeled the cross frames, and we have modeled the pier cap along with the pier. Now the task remaining is to model the abutments on the left and the piles. For modeling the abutments, I will again use the extrude feature, and I will extrude the line elements into the planar elements. So for extruding the line elements into the planar elements, I will select the line elements first. So I'll do the same thing on the other end of the bridge. So as you can see here, I'm selecting the elements, the single elements, and I will select the extrusion type as line elements to planar element. I will check off remove the source because I don't want to remove the cross frame at this location, and I will define the material, which is grade C4000, and now I need to define a thickness. The thickness can be defined either by going into Model, Properties and Thickness, or I can just define the thickness here itself by clicking on this option, and I can define the thickness. So let's say the abutment is 3 feet thick. I can define the thickness as 3 feet, and the abutment is 10 feet deep. So I will define the extrusion direction as the direction of gravity. So I will extrude it in 0, 0, -2, and I will extrude it by 10 number of times. So the total depth will be 20 feet. So in this way you can see that I have extruded the line beam elements into the plate elements by selecting the extrude feature of Midas Civil. And now I want to create the pile elements. For that I will select the nodes at the bottom of the abutment, similarly I will select the nodes at the bottom of other abutment, and I will extrude the node to line element. I will select the material as grade C4000. the section as 3 file section, and I will extrude it by 20 feet again. The depth of the file is 20 feet, and this is how the full structure looks like. Now let's say you are not satisfied with the meshing of the plate elements because the element size is like 10 feet by 2 feet, and which is a sort of a big element as far as the finite element analysis is concerned. So what I'll do, I will do the meshing of the plate elements. So I'll go to Model, Mesh, Auto Mesh Planar Area. I will select the planar area option here, and the planar area can be selected by selecting elements by identity and selecting the plate elements. So in this way, all the plate elements that are in the model will be selected. If you want to select it by single selection field, then you can just create a rectangle outside the plate elements and you can select the plate elements like this. But the simplest way is to go to the select elements by identity, the element type as plate, and the plate elements will be selected. Now I will define the type of meshing as quadrilateral plus triangle and the number of divisions as 4. So I'm dividing each element into 4 smaller elements, and I will provide the material and thickness, and once I click on apply, the meshing will be done. So as you can see, I have meshed the plate elements into finer elements so that I can obtain better results in the finite element analysis. So up till now, if you go back to the tutorial that I sent you guys, you can see that we have covered these many steps, and you can practice these steps by yourself, and we have done the meshing also. And now we have to model the boundary. For modeling the boundary, I'll first take you to the previous presentation in which I have summed up the different boundary features that can be used in Midas Civil, and then we will come back to the tutorial to see what all features can be applied in this model specifically for modeling the boundaries. So these are the different supports that can be modeled in Midas Civil. As you can see here, we can provide the restraint in the direction X, Y, and Z by going into the supports feature, which is available under Model, Boundaries, Supports, and you can specify the restraint in the X, Y, and Z direction, as you can see, and you can also apply the restraint in the Rx, Ry, and Rz, which are the rotations along X, Y, and Z direction. You can also specify the point spring supports which are generally used to simulate the soil conditions, and generally to simulate the non-stiff support provided by the soil we use this feature, and the soil support to the footings can also be modeled by this feature. So sometimes what can happen is you obtain the soil data from the geotechnical engineers, and based on certain code defined equations you can convert the soil boundary into springs, and then you can apply these springs to model the supports to the footing or the piles, and you can use these feature, the point spring support feature of Midas Civil, to define the supports. You can also use the surface spring supports, and the surface spring supports are again generally used to simulate the soil conditions, that is to simulate the non-stiff support provided by the soil, and generally this support is used to model the support underneath the footing. So let's say you have defined the footing as the plate element or the solid elements, then you can use the distributed spring option, and when you use the distributed spring option, Midas Civil will apply the supports to not only the nodes but at several other locations so that the distributed spring can be applied. The 4 different types of springs can be defined. You can define the nodal spring, which can be either a point spring or an elastic link, or you can define the distributed spring. And here you don't need to enter the properties of individual springs. You can just enter the subgrade modulus of the soil in the X, Y, and the Z direction, and Midas Civil will automatically calculate the stiffness of the spring to be assigned for assigning to the boundary. Further, you can use the elastic links. The elastic links can be used to connect two members via springs, and especially they are used to simulate the bearing characteristics. So as you can see here, this is the superstructure, which is the girder, and I want to have the bearings which are connecting the piers to the superstructure. For that, I will assign the elastic links between the two nodes, which I will define at the location of the bearings, and I will connect the two nodes that I have defined for the bearings rigidly by the node of the deck. So this is how you can define the bearing support to the deck. You can use the multilinear type of elastic link, which is generally used to model the ballast characteristics. So if you're going for a rail bridge, then you can model the ballast using the multilinear type of spring elastic link, and here you can define the P delta curve, and based on this P delta curve the analysis will be performed. You can specify certain beam and releases which can be used to do certain types of maneuvers in the model. Let's take a very simple example of the composite girder bridges, in which the girders are simply supported in first stage, and then when you apply the deck on the top, when you pour the concrete and the concrete hardens for the deck, the girder becomes continuous because of the composite action. So you can simulate that action by using the beam and releases in the program. So as you can see here, I have shown you that in the first stage, before the girder becomes continuous, they are simply supported, and this is the bending moment profile that you will obtain. But after the girders become continuous, they will have certain negative movement, hogging movement at the mid supports, and this is how you will obtain the hogging bending moments. So what you can do, you can first assign the beam and release at this stage, and you can remove the beam and release at the further stage to simulate this kind of a behavior. You can use the rigid link, which can be used to connect the two parts of the model rigidly, and you can specify the rigidness in dx, dy, dz, or the rotational rigidity in x, y, and the z direction can be defined by this option. You can define the node local axis. Sometimes the model is skewed, and as you can see in this example, the direction of the node, the global direction of the node will be in the x direction, y direction, and the z direction as the global direction of Midas Civil is. But the element is not in the global x direction. So if you want to define the translation restraint in the x direction in the field, it would be along the element. So what you can do, you can define the node local axis along the element, and then you can define the restraint in the x direction, and it will be the true restraint that you have assigned in the field. The effective scale factor can be assigned, and you can assign a scale factor for the moment of inertia about the y-axis, and you can also change the z, which is the distance of the centroid from the top or the bottom, for the determination of sectional stresses. The effective scale factors can be automatically applied for the ASTO LRFT code by going into Model Structure Wizard, PSC Bridge Wizard. We'll talk about the load cases afterwards, so let us see how we can employ these different types of supports that are available in Midas Civil for our current model. So this is the model that we have modeled so far. For the piers, I will assign the restraint in the x, y, and the z direction, and the rotational restraint will also be provided. So I will select D all, which is the restraint in the x, y, and the z direction, and I will assign the rotational restraint in the x, y, and the z direction, and I'll click on apply. So you can see that I have assigned the restraint in x, y, and z and the rotational restraint to the bottom of the piers. And if you have a footing beneath the piers, you can assign a footing also, but for making this bridge a little bit simpler, I have removed that support, removed that pile support at the bottom of the pier, and I have just used the restraint in the X, Y and the Z direction and the rotational restraint. Now I want to assign the supports to the abutment. The supports to the abutment can be assigned by two options. The first option is to see the soil characteristic and then make the point spring supports according to the soil characteristic, or the second option is, in Midas Civil we have an automatic feature known as the integral bridge spring supports. With the help of this feature, you can specify the abutment spring and the pile springs automatically by the program. So what you have to enter is, you have to enter the parameters for the soil, and once you enter the parameters for the soil and the parameters for the abutment, the springs will be automatically generated. So let us define the support for the abutments on the left and the right. For that, I will first select the elements for the abutment on the left. So here I have selected the elements for the abutment on the left. I will select the nodes for the footing, because at the bottom the springs will be assigned in the global Z direction also, because it will have certain bearing capacity. The soil will have certain bearing capacity. So I'm selecting these nodes so that I can assign the restraint in the Z direction representing the soil. So I have selected the nodes for the footing. Now I will assign the abutment height data, which is 20 feet, the width of the abutment, which is 40 feet, the length of the deck, the void ratio of the soil, the specific gravity of the soil, the cycle factor, the thermal expansion, the differential thermal expansion between the deck and the abutment, and if you have defined a material, you can take the alpha directly from the material. For the footing base, you can select the width of the footing as 3 feet, because the thickness of the footing is 3 feet, and you can provide the foundation bearing pressure. So I'm taking a characteristic value which is 1356 kips per feet square, and once you click on apply, as you can see, the springs have been assigned to the abutment as well as the footing for the left abutment. Similarly, I will do the same task for the abutment on the right. So I will select the elements for the abutment on the right. So here I have selected the right abutment, and all the properties will remain the same because the abutments are identical, and I will select the nodes for the strip footing and click on apply. So in this way you can see that I have assigned the supports, the soil supports, to the abutments on the left and the right. Now the last task is remaining is to define the supports for the piles. The support for the piles can be defined by going into the pile spring in the integral bridge spring supports, and here you can define the properties of the soil, and Midas Civil will automatically generate the spring supports for the piles. It will generate the skin friction support. As you can see, the red spring implies the skin friction of the soil, and the restraint in the transverse direction can be simulated by another spring. So now I will put the distance, the ground level, the pile diameter, which is 1 feet, the unit weight of soil, the coefficient of subgrade reaction, the friction angle, and now I will select the pile elements. The pile elements can be selected by going to the section, select by section option, and selecting the pile section. So you can see that the pile sections have been selected, and once I click on apply, the supports for the piles have been assigned. So in this way you can assign the various supports to the bridge. You can use various options that are available under the boundary option here, and you can assign the supports to the bridge. Let's check the works tree now. As you can see here, we have the point spring supports, and when you go to properties, you can see what is the property of the spring stiffness in the X, Y and the Z direction. So if you are not satisfied with this spring, let's say you want to change some parameters, you can change it. So the integral bridge support that you have assigned, once you have assigned it, you can modify it. You can modify at any point of time you want. There is no such limitation that you cannot modify it. So that was all about the boundaries that we have assigned to this bridge. Now I want to model the loads on this bridge. Now for modeling the load, I have several options. So first we will see what all options that we have for modeling the load in the bridges in Midas Civil, and then we will apply those load cases to our current project. Now talking about the static load cases, in Midas Civil we can apply the following type of static load cases: the dead load of components and attachment, the dead load of wearing surface, creep, shrinkage, etc. The self-weight can be automatically applied in the program by defining the self-weight feature. So you can just assign the self-weight in the Z, X or Y direction wherever you want. You can assign a factor to it. So let's say you want to take 50% extra self-weight, then you can specify the factor as -1.5 in the Z direction, and the weight will be amplified by 50% for performing the analysis. You can assign the specified displacement of supports. In Midas Civil, you can select a node and you can specify the specified displacement to that support to perform the settlement analysis. For performing the automated settlement analysis in Midas Civil, you can assign the different settlements to different nodes and then you can perform the analysis. So here, as an example, let's say I have the 4 supports to this bridge and I expect the settlement of 5 millimeters at end A. In the piers, I expect the settlement of 8 and 10 millimeters, and on the right end, I expect a settlement of 10 millimeters. So what I can do, I can specify these settlements in the settlement analysis data, and Midas Civil will automatically generate the combination to obtain the maximum combination, because we know that if the structure settles by 10 millimeter from all supports, there are not going to be any stresses in the bridge. But if the settlement of this node is 10 millimeters and this node is 0 millimeter, then it is going to have very high stresses. So this settlement analysis data will automatically combine the different settlements for different nodes to give you the maximum stress due to settlement. You can specify the beam load as the element beam load or the line beam load, or you can have the special distribution for the element beam load in this format. Now let me tell you a brief difference between the element beam load and the line beam load. Element beam load, let's say you have defined a trapezoidal profile for element beam load and you selected the different elements. So that trapezoidal profile of the load will be applied to all the elements that you have selected. But let's say you have created a beam element which is 10 meter long by using 10 different finite elements. So the length of each element is 1 meter and you are going to model the 10 meter long beam element by those 1 meter elements. And the profile of the load on the top of that beam element is trapezoidal. So for that you don't have to define the different load profile for different elements. What you can do, you can select the set of element on which you want to define the load and you can create the trapezoidal profile in the program, and then the trapezoidal profile will be applied to all those 10 elements together. So it will not be individual trapezoid on each element, but it will be a global trapezoidal load assigned to the 10 elements. If you want to perform the wind analysis on the structures, you can use the option uniform pressure available inside the element beam loads. You can select the load type as uniform pressure, and what this option does is, based on the exposed area of the element, it will calculate the wind pressure, it will calculate the wind force on that element, and it will perform the analysis. So let's say the wind pressure is 3 kilonewton per meter square, or let's say the wind pressure is 3 kips per feet square. Now based on the exposed area of the element, the force will be calculated on the element. So you have two options. First is you can calculate the area by yourself manually and then you can apply the element beam load to the element. Or the second option is you can just define the pressure, and based on the exposed area of the element, Midas Civil will automatically apply the wind load on the structure. And let's say you have a noise barrier. The noise barrier is not a structural component of the bridge, so we cannot model the noise barrier, but when the wind blows, the noise barrier acts as a resistance to the wind, and hence because of this resistance, this force will be transferred to the deck and to the piers of the bridge. So for that, you can check on this option, additional edge from the top, and you can specify the height of the noise barrier, and based on the height and area of the noise barrier, Midas Civil will automatically generate the pressure load on the noise barrier, and it will apply an eccentric load on the deck because of the noise barrier. So you can take into account the noise barrier wind load by using the uniform pressure load. You can specify the plane load. The plane load is a bit different from the area load because the plane load can be applied as a patch load. So let's say I want to apply a pressure load on a plate element. So if I apply the uniform pressure on the plate element, then it will be assigned all through the plate. But let's say I want to assign this type of a load which is present halfway in these plates and full in these plates. So what I can do, I can define the plane load and I can assign this patch load to any plate I want. So when you specify, again, the difference between the pressure load and the plane load is that the pressure load will be uniform throughout the plate. If you want to model the pressure load in half width of the plate, it's not possible, but with the plane load it is possible. Also, you can specify the temperature load to your structure. You can specify the system temperature, the nodal temperature. You can specify the beam section temperature. So let's say you want to specify such a profile of the temperature along the section. You can specify this profile in Midas Civil. So I'm going to talk about the temperature load extensively in the tutorial, and the moving load will be discussed later on. So let us apply the loads to this structure. So first of all, I'll define the static load cases. Let me go to the tutorial and let's see what all loads that we have to define. So I will define the self weight, the dead load, and I will define the temperature gradient load and the system temperature load. So for that, I will define the self weight. So right now I am just giving the name to the different loads. So I'm defining the temperature gradient load, which will be a temperature gradient type of load, and then I'll define a system temperature load. So in this way, if you go to the worktree now, you will see that the 4 static loads have been defined, but there is no definition inside the static load. The definition will be done by choosing different options. So first of all, I'll define the self weight. I will define the self weight in the direction of gravity by 1, applying a factor of 1. And now when you go to the worktree, you will see that the self weight has been assigned. Now I want to apply the barrier loads. For applying the barrier loads, I will apply the barrier load eccentric to the different part of the superstructure. So for that, I will check on the eccentricity. I will check on the eccentricity in the local y direction. Now let me go to the tutorial and see what all definition that I have assigned in the tutorial. So you can see that you have to select the load group name as barrier, the load type as uniform load, and you have to select certain elements so that you can apply the barrier load on the top of those elements. The eccentricity is 5 feet and the load value is 2 kips per feet, and I will first select, okay, let me close this, and I will select the section. So I will select the composite section so that I just have the composite section to work with. And now I'll go to load, element beam loads. I will define the load case name as barrier load. I will define the load intensity, the eccentricity, and this load will be assigned to the outer elements only. For that I will select this option, which is easy to select the curved element. So as you can see here, I am creating a line so that I can create the external elements, and now when I click on apply, you can see that the eccentric load has been applied to the girder element. Similarly, I will assign the barrier load on the left side of the bridge, on the left girder of the bridge. For that I will define the eccentricity as -5 feet, and I will again select the elements by as you can see here, the elements have been selected and the load has been applied. So this is how I have applied the barrier load. The barrier load is applied as an eccentric load to the outer elements. If I activate the whole structure, this is how the whole structure looks like. After the barrier loads, you can apply the wearing course load, you can apply all other types of load that you want to apply, but here I would just cut the dead load definition up till barrier load, and now I'm going to define the system temperature. So let's see what is the effect on the structure if the temperature increases by 30 degrees Fahrenheit. So for that I will go to load, temperature loads, and system temperature, and I will define the system final temperature as 30 Fahrenheit. I will put it under the load case system temperature, and when you specify this load case, MyDecibel will automatically take into account the expansion of the elements and the stresses developed due to that expansion because of the change in temperature. Now I want to define the gradient section temperature load, and I have used this type of a section. As you can see here, the beam section temperature changes from 12 Fahrenheit to 0 at a depth of 0.5 feet from the top, and from the bottom it changes from 10 to 5, from the depth 0 to 0.4, and then from 0 to 0.6 it changes to 0 from 5. So I will define this definition in the program, and then I will assign this to the elements. For that I will go to load, temperature loads, beam section temperature, and I will select the type of element as pre-stressed concrete or the composite type of element. Now here you can specify the elasticity and the thermal expansion coefficient either by element. So what all material that you have assigned to the element, it will be automatically taken from that material, and if you want to specify input, your own input, you can choose from here. Now you can take the reference from the top or the bottom. So I want to define this profile, so first I will take the reference from the top, and then I'll take the reference from the bottom. So first I will take the reference from the top. Now comes B. Now the B is the characteristics value of the rectangle that the program will take for obtaining the thermal stress values. For that you can take the B from the section automatically, so the program will automatically take the B from the section. Now let me talk about this B for a while. As you can see, if you take this portion of the section, it has this profile, it has a web, it has small part of the flange, the top deck. So it will have a certain area. What MyDecibel does is it converts this area into a rectangular area based on B that you have defined, and whatever B we get and multiply it with the depth of the temperature, it will determine the thermal stresses. So for that I'm just defining the temperature profile along the section now. So from reference from the top, from 0 to 0.5 feet, the temperature changes from 12 to 0 Fahrenheit. And now I'll change the reference to bottom. From 0 to 0.4, the temperature changes from 10 to 5. And from 0.4 to, let's say, 1 feet from the bottom, the temperature changes from 5 to 0. And now I'll assign this type of beam section temperature to all the elements having composite section. So I'll select the composite section and I click on apply. So in this manner the beam section temperature has been assigned to the composite sections. Now talking about the moving load analysis, in Midas Civil the moving load analysis is performed in 3 steps. First we define the code for which you want to perform the moving load analysis, then you define the lane, and then finally after defining the vehicle you can perform the moving load analysis. Now let me briefly talk about the moving load analysis here and what are the different types of moving load analysis that you can apply on the bridges. So here when you define the lane you have 2 options. The first option is the vehicular load distribution can be done by the lane element, and the second option is cross beam. When you define the vehicular load distribution as lane element, then the vehicle load will be applied to the element on which the lane is assigned as an eccentric load. And if you select the vehicular load distribution as cross beam, then the load is first divided into the cross beam. As you can see here, this is the cross beam, and then it is transferred to the surrounding elements. Now let me tell you when to use what kind of vehicular load distribution. Let's say you have a segmental post tension type of box girder bridge. Then you can use the lane element, because in the box girder bridge, if it is a single cell box girder bridge, we generally model that kind of a section using a single section, and we model that element using the line beam element, and we assign the section properties of the box section, the single cell box section, to that element, and there we can use the line element vehicular load distribution for performing the moving load analysis. The cross beam type of vehicular load distribution can be applied when you go for the grillage model. The grillage model or the composite bridges will have the vehicular load distribution transferred from deck to the girders, and hence this action, as you can see, the P is the wheel load, and this P will be transferred from the deck to the surrounding steel beams, and then this is how the inference line will be obtained for performing the moving load analysis. So this is how it is performed. Let's say you have the vehicle wheel load here, and this is the grillage model. These are the cross beams, this is the main girder. Then first it divides the wheel load into the surrounding cross beams based on the simply supported beam approach. So if it is 100 kilonewton, 75 will go at B, 25 will go at A, and then it will be transferred to the main girders. So this is how the load is transferred. So you can see the load here, it is transferred to the surrounding cross beams and then perform the analysis. So let us define the moving load analysis data in our program to perform the moving load analysis. So for that I will go to load, moving load analysis data, moving load code, and I will select the code as ASHTO LRFT, and now I'll define the lane. For defining the lane, I need to set up the lane parameters. So I'll define lane 1. I will define eccentricity. For simplicity of this bridge, I'm just defining 2 lanes, and I want to have the vehicular load distribution as cross beam type. For having the vehicular load distribution as cross beam type, we need to define the cross beams first. For defining the cross beams, I will select the cross beams, which are the transverse section beams representing the deck. I will double click on the transverse section and all the elements will be selected. I will go to the group. I will create a new group for cross beams, and I will drag and drop this group on the top of these elements, and now I have a structure group named cross beams for performing the moving load analysis. Now I can define the moving load lane. So lane 1, the eccentricity will be 0. I will define the element as cross beam, the vehicular load distribution as cross beam type of vehicular load distribution, and I will choose 2 points to define the lane. But here the 2 points option can only be used if the bridge is straight or a bit skewed. So what I will do, I will define the lane either by picking, I will pick individual elements and I'll define the lane accordingly, or I can just define the number along the elements and the lane will be defined along those elements. So let us see what is the number of elements along a particular girder, and then we can define the lanes along that girder. So you can see for girder number 2 the element number is 42 and it runs from 42 to 81. So I can just define 42 to 81 here, and I can specify eccentricity if I want, and when I click on add, the lane will be defined along the profile of the element. Similarly, I will define lane number 2 and I'll define the lane number 2 on other beam element. The starting number is 122 and it goes up to 161. We'll click on add again. The elements will be selected and I click on OK. So in this way you can see that I have defined two different lanes, and this is how the lane looks like. So they have been defined along the elements. Because the elements are curved, the lanes will be curved, and this is how the lanes have been defined. So if your bridge is curved, you can define the lane in this manner. If the bridge is straight, you can define the lanes by clicking on two nodes to define the lanes. Now I will define the vehicle. So I'm defining the dynamic amplification as 33%. The vehicle has been defined. Now I will define the moving load case. The moving load case can be defined by combining the vehicle to the lanes, as you can see here. And now I click on OK and the moving load case has been generated. Now let me talk about the moving load case that we have just generated. In here you can see that we have the subload case option, in which the loading effect can either be combined or independent. Now let me explain to you what is the difference between combined and independent. For that I will go to my general presentation and I'll show you when you can use the combined or the independent option. Let's say we have a bridge, a hypothetical bridge in which we have a train lane and a vehicle lane. Now we cannot assign the vehicles the lanes in which the vehicle is supposed to move to the train lane, or we cannot define the train to the vehicle's lane. So what we have to do, we have to define the train load and we have to define the vehicle load individually, and then we need to define two different lanes for vehicle and train. But in reality, the train and vehicle can move together. So what we will do, we will define two subload cases, one for vehicle, one for train, and we can combine them together to obtain the result. So here what I'll do, I will select the option combined and I will combine the individual results for vehicle and trains so that I can obtain the maximum bending moment, which will have the effect of train and vehicle together. So this is how you can use the combined option. But the independent option can be used when you want to perform the transverse analysis. So what you will do, you will put the lanes at several transverse locations. So let's say you made a set of you made 5 different sets of lanes to perform the transverse analysis. Now what you can do, you can create 5 different subload cases and you can choose the option independent, and then the program will give you the maximum out of those 5 subload cases. So the program will determine the results for individually for those 5 subload cases, and then it will show you what is the final result, the final maximum value. Also in Midas Civil you can simulate the hydrostatic or earth pressure load in the lateral direction by defining the pressure. Now let me go to the program now and I will define the lanes for the negative support. As we know that the AASHTO code specifies that we need to take into account the 90% load of 2 trucks
for determination of maximum hogging bending moment. So this is the AASHTO LRFD section 3.6.1.3.1, and it says that for both negative moment between the points of counterflexure under the uniform loads on all span, 90% of the effect of two design trucks spaced at a minimum distance of 15 meters between the lead axle of one truck and the rear axle of the other truck, combined with the 90% of the effect of the design lane load, should be used for performing the analysis. For taking into account this clause of AASHTO LRFD, you can choose the option lane supports for negative moment. Now let me go to the program and I'll show you how you can define it. You can define the lane supports negative moment at interior piers, and you can either do the auto input or you can do the user input. In user input, you can define the regions where you expect the hogging bending moment, and then when the program will determine the hogging bending moment at those locations, it will take into account the 90% weight of two trucks. Or you can go for the auto input. In the auto input, what you can do, you can first select, let me select all the elements for the cross beams, for the composite beams. So I have defined a structure group known as girder group, and now I'll put this girder group into the lane support negative moment. Now what this girder group does is, it first performs a static analysis, let's say based on the self weight, and it will see what are the locations of the hogging bending moment, and based on that location, when the program will perform the moving load analysis, it will automatically assign two trucks at the location of the hogging bending moment. So let me assign the girder group, and in this way, in the works tree, you can see that I have assigned the lane support negative movement at the girder group, and Midas Civil will automatically take into account the effect of two trucks for determination of hogging bending moment. So in the tutorial that I have provided you, we have covered up till this step, and now we can perform the analysis. But before performing the analysis, we need to delete the first node that we created, because that node was only for the reference. We needed the radii distances from that node, so that node is of no use to us now. So what I'll do, I will unselect all the elements, I will select the node 1 and I'll hit delete. So in this way we have deleted the first node, we don't need it any longer, and we can save the project and run the analysis. I'll not run the analysis here, I will just open a pre-analyzed model so that I can show you the results. These will be the different results that I'll be showing you. You can see the results by going into result, forces, beam diagrams, and obtain the various diagrams. So let us see the beam diagrams for the self weight. So you can select the static load case as self weight, check on the legend, and this is how you have obtained the self weight bending moment. If you want to obtain the tabular result, just click on this option here, select the elements, select the load case, and once you click on apply, the tabular results will be obtained. Now let's see what is the effect of temperature on the structure, and let's see if the system temperature changes by 50 Celsius, how does the axial force changes. So this is the effect of temperature, 50-degree increase in temperature, like this. Let's see the stresses in the abutments due to self weight. So here, this is how the stresses in the abutment look like. You can zoom in at a particular location and you can see how the stresses in the abutment looks like. Now let's see what is the axial force in the piles. For that, I will just activate the pile elements, and I'll go to result, forces, beam diagrams, and I'll select the axial force and I'll check on the legion, and this is how the file force looks like. Now let us check the results for moving load analysis. The moving load analysis results can be obtained in the beam diagrams. If you select MV max, it is the maximum sagging bending moment envelope obtained due to the moving load analysis. MV min implies the maximum hogging bending moment. So you can see what is the hogging bending moment envelope due to moving load analysis. And if you want to obtain the influence surface, influence lines, then you can obtain the influence line. Let's say I want to obtain the influence line for bending moment in element number 25. Then this is how the influence line looks like. So all the results are very intuitive. You can just go to result, influence line, you can obtain the influence line. If you want to obtain stresses, you can go to stresses, obtain the stresses. Now let me show you a very special feature of Midas Civil known as moving load tracer. You guys must have used it already, but let me just remind you about this feature. This feature tells you the location of the vehicle for obtaining any effect on a particular element. So let's say I want to obtain what is the maximum bending moment at element number 25 and what is the vehicle location for the same. Now once I hit apply, you can see that the maximum sagging bending moment at element number 25 and the end eye of element number 25 is obtained at this location of the vehicle. And now you can convert this static file, this load case, into a static file, and you can invoke that static file as a static load, and you can perform the analysis based on that load. So whatever load that we see here, it will be converted into static load, and you can obtain the you can perform the analysis based on that static load. Now as a part of verification, let's see if the program applies the correct it takes into account the AASHTO procedure that the two trucks must be taken into account for obtaining the bending moment at a mid support. So here I will select the key element as 108 and I will see what is the location of the trucks for obtaining the maximum hogging bending moment, because it is an element on the mid support. So this is the element number 108. Let me highlight that element for you. So this is the element number 108, and you can see that these are the two trucks that have been used for determination of maximum hogging bending moment, and the AASHTO code has been followed for obtaining this hogging bending moment value. So this is how you can obtain several results from Midas Civil. If you want to obtain any result table, let's say you want to obtain the result table for bearings, because we have applied the bearings on the top of pier caps connecting the piers and the superstructure, you can obtain the bearing force by going to result tables, elastic link, and you can select what all elastic link do you want, and here you can obtain the forces and the bearings. So these are the forces and the bearings for the bearings model on the top of pier cap connecting the superstructure, and based on this force value for the bearings, you can just go to the bearing manufacturer and you can obtain the proper bearing for your bridge. So this is how you can do the simple analysis of bridges in Midas Civil. I've shown you the geometry from starting from 0 until I finish the project, and I think you can use the same modeling features in your upcoming projects for modeling this type of bridges. And I have used a very complicated bridge profile, and that's why I had to use element by element modeling, but you must have appreciated that it's not very difficult to do the element by element modeling still in Midas Civil, because of the excellent GUI features of our software. Now it's time to take the questions from you guys. If you guys have any question, then you can ask me the question right away.